In this video, I'm going to discuss an important theorem called the mixed partials theorem. This theorem is sometimes also known as Clairaut's theorem, okay, some French mathematician from the 19th century. Okay, now, here's the theorem. Assuming that I have the following mixed partials, f sub x y and f sub y x, right, exist in an open disk of R squared, the xy plane. These two mixed partials are equal if they are continuous. In other words, continuity implies commutativity. Okay? Continuity implies commutativity. This is the mixed partials theorem. Let's show examples of something like this here. Okay? Now, something we need to be a little bit careful on, make sure we understood our notation here. Sometimes students get a little mixed up on this. Z is a function of x and y, okay? When I go the partial derivative of, with respect to x of f, notice that my notation here with my partials are in front of the f, right? Okay, so I'm taking partials with respect to x of f. It's also written this way. But then I've got what? My subscript notation also. Okay? Now, if I'm going to do this, if I'm going to take the partial derivative with respect to y of the partial derivative of f with respect to x, notice that I'm actually computing what first? The partial derivative with respect to with respect to x first of f, and then taking what? The partial derivative of that result with respect to y. This is how sometimes people will write it, like this, notice. Okay, so I've got a del squared up here, or nabla squared. That means you're taking a second derivative. But notice it's kind of written backwards if you're reading a book, from left to right. You're actually differentiating with respect to what? X first, and then what? Then with respect to y. Okay, so that's just a little bit of the notation here. Notice the subscript notation, it's actually clearer if you're like reading a book, reading from left to right. You're, differentiating with respect to x first, and then taking that result and differentiating with respect to y. Okay? Likewise, if I turn this around and I take the partial derivative with respect to y of f first, and then take the derivative with respect to x of that result, then it's going to look like this. But with subscript notation, it would be f sub y, then x. Okay? All right? So do you see how to interpret this? F sub x, x, y, y, x. Okay? In terms of nablas or dels. Okay? First you're differentiating with respect to x, so I've got to have this, and then I'm doing it again. Okay? And then I'm taking that result and I'm doing what with it? Differentiating with respect to y, and then with respect to y again, and finding that result, I'm differentiating with respect to x. So this is sometimes written this way because these are in, one right after each other. We go partial, or del to the fifth, partial with respect to x. That came first. There was two of those, so we have squared. And then what? Two y's in a row with respect here we've got 2, so we have a squared, and then we finally take that result and differentiate with respect to x. Now, Clairaut's theorem can actually be generalized here, so that if all the partial derivatives, mixed partials involved, are continuous, then you actually they will end up being equal to each other. Okay? That's not really obvious, but it is true. Okay? Let's take an example here finally. Okay, had to get that notational stuff out of the way first. Okay, suppose I have f sub xy is x cubed minus 3x squared y plus 7x plus 6y plus 13. All right, let's differentiate with respect to x first. We would get what? 3x squared minus 6xy plus 7. Okay, if I go f sub xy, that means I'm doing what? I'm taking the result above and differentiating with respect to y. So that would be 0 minus what? 6x plus 0. So that will boil down to minus 6x. Okay, let's turn it around. Okay, f sub y first. Okay, let's differentiate the original function with respect to y first. We would get what? Negative 3x squared. 0 there, plus 6 and 0 there. Yes, we would get negative 3x squared plus 6. Okay, differentiate that with respect to x, and we get what? Minus 6x. Okay, all these functions are continuous, so they are going to be equal, these mixed partials, and in fact, you notice they are. We get negative 6x in both cases. Okay, so that's a fairly easy theorem. Students almost always remember it, but what's the shorthand version of this then? Continuity implies commutativity. Okay, remember commutativity, I'm referring to the operators involved, the differential operators differentiating with respect to x or y or whatever it might be. Okay, there's the mixed partials theorem. All right, well, hope you understood that. Feel free to use that theorem then.